All right, folks, welcome back. I hope that everyone is okay again. Hope that you all had a chance to take a look at the work that we had yesterday. I think that was pretty straightforward. Let me go ahead and let me set my timer here really quickly so that I don't overshoot my time. I think the time limitation that we've been working with right now works pretty well. So let me go ahead and set it for 20 minutes. Sorry, hold on one second here. Um, and I'm going to try to stay on that time schedule right now, okay, and use that to kind of give you an opportunity to get the work done in class here during class time here as well. Okay, just a quick reminder, really, as we go through today, folks. As we go forward, tomorrow was a scheduled in-service day for teachers, and so that's still in place. So we will not meet tomorrow. Um, just keep that in mind as we. So you have basically tomorrow off, so make sure you keep that in mind. And then we'll meet again on Monday. Okay. Um, Outside of that, like I said, nothing new. I hope, like I said, all is well. That you folks are all feel well, and your families as well. But let's go ahead and let's continue on then, and let's quickly review where we left off with yesterday. Yesterday, we were talking about the bond energies of a covalent bond. So each covalent bond has a certain bond energy associated with it. Those bond energies, remember, we learned back on Wednesday, I'm sorry, Tuesday, was that these bond energies are the average bond energies of, and so we use those to help determine then the amount of energy that's either going to be released or absorbed when they either form or when they break, respectively. So when bonds break, they're going to need energy to break it, and when the bonds form, they're going to give off energy, which makes sense based on what we've been talking about up until this point. Excuse me, and that is atoms only form bonds. Atoms will only form bonds if they will end up at a lower energy state. And the only way they're going to end up at a lower energy state is if they give off energy. That is if the reaction is going to be exothermic. The bond formation is going to be exothermic. Now we can get bonds to form if the process is endothermic, but then what we have to do is we have to put energy into it. And we'll learn later on that processes that are spontaneous will be exothermic, which means they give off energy, and processes that are endothermic are going to be non-spontaneous. So again, we can force a bond to form that is going to be that is not favorable, that is not going to be exothermic, but then that requires energy. Okay. All right. So what we learned, and so from there, what we did was we were able to take those bond energies and use it to find the energy associated with a particular reaction. That is, we can calculate, determine then whether a particular reaction will be exothermic or endothermic. And we were able to do that using a very simple formula where we have to total up all the bond energies of the reactants, and then we total up all the bond energies of the product. We subtract the two of them, and we get our value. Okay? And so we did a couple example problems yesterday in class, and I asked, and we left off with I asked you to do number 66A and B. So what I'd like to do is I want to do 66A with for you right now. So let's go ahead and do 66A. Okay. So let's do 66A, and this will help us to segue into what we will be talking about today, which are Lewis dot structures. And I had a discussion with Henry yesterday, and as I pointed out to you in lecture, we have to be able to draw these structures. And if you don't draw these structures, it'll be hard to find out what type of bonds form and what type of bonds break. And so I asked you yesterday to make sure you review the Lewis dot structures from last year. We'll talk about Lewis dot structures today a little bit more as well, but the discussion today is going to go a little bit faster because I'm assuming you all remember how we draw the Lewis dot structures. Okay, so make sure you review that or come by today after school and get that extra help if you need it. Okay, but in 66A and B, they give us the reaction already. They give us the structures already. However, they could have given us this. They could have given us just the formulas. Okay, so that would be the formula for the first one as a gas, and they were saying that that particular compound reacts with this particular compound here. Okay, to form this compound. Okay, which again gives us very little information about the structure, and we need to know the structures. These are the formulas here, and then we can balance out the reaction that way. Okay, it'd be very hard, and they wanted us to find then, and then they would ask us to find then the delta H, the enthalpy for this reaction. Okay, so it'd be very difficult to calculate that enthalpy if we didn't know what type of bonds were held here. So we'd have to be able to draw the structures. Now, in this particular problem, they give us the structure already. So for this compound here, we have a single bonded hydrogen. Sorry, using a new board here. Single bonded hydrogen to carbon, which is then triple bonded to nitrogen. And they leave out the fact that there should be a lone pair right here and right there. Okay, so that'll complete the octet for nitrogen. We'll review that today, folks. Okay, and then hydrogen then is going to be a single bonded, single covalent bond between the two hydrogens there, and we have two of those. Okay, so two of those form, two of those. Okay, on the right-hand side then, what they give us is the structure of this compound, which is a methyl group, which is a three hydrogens attached to one carbon, which is then attached to a single bonded nitrogen, which is then attached to two hydrogens as well. Okay, so this is the structure, and then lone pair here, lone pair here, and lone pair there. Okay, all right, so that's the structure right there. We need, so they gave us the structure. We need that structure in order to do our calculation. Okay, so we need our structure in order to do that calculation. All right, so we'll learn today how to draw these structures. These are the Lewis dot structures that I've been talking about. So we'll learn how to do that. But for this problem here then, what you'll need to do then is you need to find the bond energies. Okay, so you'll need to refer to a table, and I'm gonna write in the bond energies for you, but for the homework that you had to do, hopefully you recognize it, you had to refer to table 8.4, which was on page 374 in order to get these values. Okay, all right, so let's go ahead and identify these bond energies here. So this is a carbon hydrogen single bond. From that table then, we are told that that bond then has a bond energy of 413 kilojoules per mole. Sorry, kilojoules per mole. Okay. All right, and so all of those values, all the values in table 8.4 then are all positive, because those are the values, because that's the amount of energy needed to be put into the bond to break the bond. So essentially all these values that we are writing right now are values that are needed to break the bonds. Obviously over here, these are bonds that need to be formed, and so we have to make sure that we indicate that this is a formation by in our calculation showing that it's going to be negative. Okay. Okay. This is a carbon nitrogen triple bond. It has an energy of 891 kilojoules per mole. Okay, and then we have the hydrogen single bond, and that has a value of 432 kilojoules per mole. And I'd just be curious to find out how many of you be able to answer this question, and that is, why is the carbon hydrogen single bond lower in energy than the hydrogen single bond? And just as a hint to help you with that, just think of Coulomb's law and the size of the atoms to determine to answer the question why this energy is smaller than that energy. Okay, all right. So with that said, then labeling this here again, we have a carbon hydrogen bond that's 413 kilojoules per mole. Okay, and that'll be true for that bond as well, and for that bond as well. Okay, so we have those bonds right there. Okay, and then we have a nitrogen hydrogen single bond, and so that was I think we were given that's 391 kilojoules per mole, and that applies to that bond as well. And then we have one carbon nitrogen single bond, and that's 305 kilojoules per mole. All right, so those are all the bond energies that we obtained from the table. Okay, and so let's go ahead and work that out. Okay, let's go ahead. Now we want to be able to find delta H for this reaction, the enthalpy of this reaction. So therefore, delta H then is going to be equal to, and let me just write this down for you, the sum of all of the bonds all the bond energies. Now, and I'm sorting this bond for the reactants. Okay, and times the number of bonds, because that's basically the number of moles of the bonds, minus the sum of all the bonds for the products, the bond energies for the products, okay, times the number of bonds present. Okay, so this is the bond energy and this number of bonds, or the moles of those bonds. Okay, and so that's what we have there. So remember, this Greek letter sigma means just to add it all up. Okay, all right, so let's go ahead then and let's add up what we have. Okay, so starting with the reactant side first. Okay, so we have then with the reactants, we have one carbon hydrogen bond on the reactant side. So that's going to be 1 times 413 kilojoules per mole. Okay, we have a 1, so we're going to add to that 1 carbon nitrogen triple bond, which is 891 kilojoules per mole. Okay, and then to that we're going to add 2. So we have 2 of these molecules. You have 2 of these bonds. We have to break 2 hydrogen single bonds. It's going to be 432 kilojoules per mole. And that takes care of everything for the reactants. Okay, so that's summing up everything on the reactants. Okay, all right. So then we have to, and remember, you got to subtract here. We have to sum up everything for the product, and I'll write it underneath here. Let's go ahead and do that. Okay. So we have 3 carbon hydrogen bonds on the right-hand side. So we have 3 carbon hydrogen bonds that form, but just write down this number here. So that's going to be the positive value. This negative here will make it, this negative sign here from the equation will make this negative, okay, which means in this side, this is exothermic and that's endothermic. Okay, so we have 413 kilojoules per mole. So again, do not include a negative sign in here. Okay. Plus, we have 2 nitrogen hydrogen single bonds forming. That's going to be 391 kilojoules per mole. And then finally to that, we're going to add the 1 carbon nitrogen single bond that forms. It's going to be 305 kilojoules per mole. Okay, and that takes care of everything on the product side. Okay, all right. Hopefully, so once you have that, you just total it up, and I think let's go ahead and let me check my numbers really quickly here. If you total up, then you get your final answer. Then it's being negative 158 kilojoules per mole, and therefore this reaction is going to be exothermic. This is this reaction can happen spontaneously with a little bit of added heat. You can get this to go. Okay, all right. Hopefully everyone's okay with that. Like I said, make sure you combine CME. If you did not get that, let me just give you the answer real quickly to 66B so you can check your own work. So delta H here is going to be negative 1,169 kilojoules per mole. Okay, so that's the answer for 66B. Okay. All right. Good. Let's go ahead then. And what I'd like to do is let's continue. Let's talk about the Lewis dot structures. The Lewis dot structures are based upon a theory of bonding, covalent bonding that we need to start out by talking about first. Okay. But before I do, just a quick word on molecular modeling. Okay. So with these models here that we propose, that is the models that we propose for the bonding. Just like any good model, just like any model, these are just our way of explaining the microscopic phenomena. Obviously, we can't see these bonds. These bonds are made from electrons. So this is our best way of explaining it based upon the data that we can collect. For example, bond energies and spectroscopic data, which I'll point out to you. We will do photoelectron spectroscopy towards the end of this chapter 9. So we have some ways of kind of determining these bonds and what they are, but it's indirect. And so from that information, then we piece together what we think is happening at the microscopic level. And so that's what provides then the theories that we come up with. Okay, so that, there's 2 theories for bonding that we will use, 2 theories for covalent bonding that we're going to use. We're going to use the localized electron model, which we will learn here, and the molecular orbital theory, which is what we'll learn in chapter 9. Both have their benefits. Both are good at explaining certain aspects of bonding, but both also present certain deficiencies as well. And so we have to consider both. And so just like with any good model, what we want to do then is that we want to make sure then that we understand it's not reality. It's our explanation of reality. They tend to be oversimplifications for the most part. And the models that tend to be a little bit easier to understand tend to be a little bit more simplistic. Okay? And the localized electron model is a fairly simplistic model, but it's an easy one to understand. And that's why we teach it here in high school chemistry. Okay? And so what we end up doing, and what we make sure we try to do, is we end up using combinations sometimes of models. And when we find that a model is wrong, finally, what we often try to do is we try to figure out what's wrong with it, and we either we modify it, and in some instances, and this is a little bit rare, we have to scrap it completely. But most models that we end up using are fairly good models. Okay? All right, and so let's talk about this localized electron model. Okay, the premise of the localized electron model is that the electrons that are shared between two atoms, the electrons that are shared between the two atoms, stay between those two atoms. Now, there could be unequal sharing. We talked about that earlier on in this chapter, but essentially then the localized electron model stipulates that whenever a bond is formed, the electrons stay with those two atoms. They don't move throughout the molecule as a whole, which is going to be a key difference between the localized electron model and the molecular orbital theory. But this is a very good model to describe covalent bonding because it's simple. Now, understand this localized electron model is only applied to covalent bonds. It doesn't deal with ionic bonding. It doesn't address ionic bonding. That's a different matter. Okay? And so with that said, then keep this in mind with the localized electron model, the pairs of electrons that are shared between atoms stay between the atoms. And so with that said, then the lone pairs then are localized to the atom that possesses those lone pairs. Okay? So like I said, the localized electron model is good because it's a very simple model to use. Okay. All right. So what we're going to use the localized electron model to help explain that is we're going to use it to explain the arrangement of these valence electrons, which is what the Lewis dot structure is and what we'll learn about in just a moment. You'll do a PhET lab next week. I'm going to ask you to do a PhET lab in place of a lecture here. I'll ask you to do a PhET lab that'll allow you to explore molecular geometry. That's the VESPER model, and the localized electron model does a good job of explaining that as well. And also we can deal with the types of atoms and the atoms that share electrons and the atoms that have lone pairs. And so what we're going to do then is we're going to focus on this part. We're going to focus on the Lewis dot structure here, and then with VESPER theory and description of atomic orbital types, we'll talk about that. And this is the hybridization that we'll talk about. Okay, we'll talk about these in chapter 9. Okay, all right. What about these Lewis dot structures? Let's quickly review this. Lewis dot structures are just structures that we use to show how atoms are connected together, how atoms are connected together, and this tends to be a two-dimensional representation of these atoms. Okay? And so the reason why atoms will connect together and the reason why they will share electrons, or how we will determine how these atoms connect together, it's going to be based upon the octet rule that we talked about, where the atoms then will try to achieve a noble gas configuration by sharing either 2, 4, or 6 electrons. And so with that said, then let's take a look at hydrogen. Hydrogen obviously will not meet up with the octet rule. So we define that rule that determines the bonding of hydrogen as the duet rule, meaning that it just forms it shares 2 electrons. And in sharing 2 electrons, then what we're going to notice happening here is that these 2 electrons here make the electron configuration for each hydrogen then 1s2 for each one of these, which is the electron configuration for helium. So instead of calling it the octet rule, I often sometimes refer to it as the noble gas configuration as well. And so in sharing these 2 electrons here, each hydrogen now obtains the noble gas configuration of helium. Okay? Helium's noble gas configuration. Okay? So that is what we refer to as the duet rule. The octet rule, on the other hand, then refers to each atom obtaining 8 electrons, and in doing so, they will also obtain a noble gas configuration Here, in this case, then each fluorine will obtain the noble gas configuration of neon. Okay? And so remember, when we talked about the noble gas configuration is the complete electron configuration. But if you notice here, the only electrons that are being shared, or the only electrons that we account for, are the valence electrons. So you have then 8 total valence electrons for both fluorines when they join together in that single covalent bond. Okay. All right, so there's 3 types of covalent bonds that we can talk about. We can talk about the single, the double, and the triple bond. Single bonds, then you have 1 pair that are being shared, or 2 electrons that are being shared between the 2 atoms. Okay, with a double bond here, we have 2 pairs that are being shared, and thus 4 electrons that are being shared. And in a triple bond, then we have 3 pairs, and thus 6 electrons that are being shared. Okay, now this is the DAS structure here. Okay. This is the DAS, sorry folks. This is the dash line structure. So instead of drawing the dots, what we're going to do from now on is we're going to draw the dash here. Each dash then represents 2 electrons. Okay, so here you have 2 electrons here and 2 electrons here for a double bond, thus our 4 pairs. And therefore each dash line here represents 2 electrons, and thus our 3 pairs, and thus 6 electrons for the triple bond there. Okay. All right, so with that said, what we do to draw the Lewis dot structures? Eventually, first of all, what you want to do is you want to sum up. That means you want to add up all the valence electrons, because in the end, you're going to count all of the atoms, all the bonds, all the lone pairs, all the electrons. They should add up to this total right here. So you want to sum those all up. Okay. Then what you want to do is you want to start pairing up the electrons. Okay, and so that the atoms will either achieve the duet or the octet that we talked about. Okay, and so make sure you keep that in mind. Okay, and so what will end up happening is that they will end up with the noble gas configuration. So each atom in the bonding relationship will have a noble gas configuration. Okay, and then with that said, then at the end, you want to make sure then that the electrons are all paired up correctly. Okay, all right. Let's do an example here real quickly. Let me go ahead and let's draw the Lewis dot structure for water. Okay, so let's draw the Lewis dot structure for water. Let me clear this out for us. Okay, and let's see what we have here. Okay, all right. So with water, then water's formula is H, and let me just do this. Go a little bit over here so we can I can get you started on this. Okay, and so with that said, then make sure you understand. Let's draw out first the Lewis dot structure for each atom. So you have a hydrogen atom there, that's another hydrogen atom there, and the Lewis dot structure for each atom, remember, indicates the number of valence electrons with their pairs and with their unpaired electrons. So make sure, if you're not quite sure how we get 2 pairs here and 2 unpaired electrons, make sure you stop by, review that in your first year chemistry book from last year, and then if that doesn't help, come by and see me. Okay. All right, so at this point then, what we want to do first is we want to connect up the dots. So it's basically connecting the dots here when we do this, okay? And so that when we connect the dots, each atom will achieve either the duet or the octet. And if we see this here, okay, if we connect it that way, then each hydrogen now has its duet met up with. So it has its 2 electrons. So you have a duet there, you have a duet there, and the oxygen here has its octet here. So each hydrogen now will achieve the electron configuration of helium. Okay, for helium. Okay, and this oxygen will achieve the noble gas configuration for neon. Okay, and so make sure then that when you get this done, that's what you're checking for. You're checking to see then that each atom then achieves its octet, and for hydrogen its duet. Okay. And so drawing the dash structure for this then, which is what we want to get into the habit of doing. So you have then 1 pair here that thus forms a single bond between hydrogen and oxygen. We have another single bond here between hydrogen and oxygen. So we have 2 single bonds connecting together water. Okay. And so to start out then, let's go ahead and count all of our electrons. I'm sorry, I jumped ahead a little bit, but let's count all of our electrons. We have 2, 4, 5, 6, 7, 8. We have a total of 8 valence electrons to account for. So let's make sure we have that here. So we have 2, 4, 6, 8. Okay, so remember each one of these counts as a pair here. So in our structure, we have accounted for the 8 electrons. The structure then is correct. Okay. All right. let's go ahead then and let's do, let's do a couple more here. Okay, so let's do these. Let's do, we just did water. Let's do phosphorus tribromide and the hydrogen cyanide right there. Okay, so let's go ahead and let me clear this out. Okay, let's do PBr first. Okay. PBr3. Okay. All right, so first of all, phosphorus, remember, has five valence electrons there. So we have phosphorus with its 5 valence electrons. That's right here. Okay. Bromine has, remember, oh, sorry, we have bromine. Each bromine has 7 valence electrons, but we have 3 bromines here. And so we're going to add those up. So we have 21, we have 26 electrons that we have to account for. Okay, so we have 26 electrons we have to account for. Now, as you do more of this, then you're going to start recognizing then the which atom's going to be the center atom. But hopefully you see then that bromine's going to, phosphorus is going to be the center atom, and if we align each bromine around the phosphorus, you're going to form then single bond between each bromine and the phosphorus. So therefore, if we draw the dashed line structure, we have then phosphorus forming a single bond with each bromine. And then make sure you include in all of the lone pairs that each atom has. Okay. And so therefore, it's 3 single bonds that form between bromine and phosphorus to form this molecule here. Okay, so let's finally count all of the electron pairs here and see if we come up with that 26. We got 1, 2, each bromine has 1, 2, 3, so we have 9, 10, 11, 12, 13. We have 13 electron pairs. Okay, it's 13 electron pairs, 2 electrons each, and that'll give us our 26 electrons. So that checks out. Okay. All right, so that's the structure for phosphorus tribromide. What I would like you to do then is I want you to draw, so what I'm going to leave you with then is I want you to draw the structure for hydrogen cyanide and then post it on your work. So that's the only assignment that I'll ask. That's the only thing that you'll have to turn in today. And so please make sure you draw the structure for this particular compound, okay? And then we'll pick up with this particular compound tomorrow. I'm sorry, Monday. And then we'll continue practicing with the Lewis dot structures. Okay, so please just draw that structure and then turn that in for your work today. Okay, all right, folks. Have a good weekend, and I will see. Have a good long weekend, and I will see you folks on Monday.